Okay, so what we're going to start today is talking about how graphs work, okay? How you build a graph. Specifically, you guys are going to build them using Google Sheets. The old-fashioned pen and paper, or actually pencil and paper method is pretty much dead, okay? And plotting them on a computer is obviously more accurate, more efficient. So we're gonna look at doing it that way, but we still have to look at the fundamentals of what's a graph for, okay? How do we calculate some things from the graph, stuff like that, okay? So obviously you're not going to have to acquire a graph paper, ruler, or pencil, and you're not going to have to draw an axis on there or anything like that because that's all going to get done for you, okay? One of the things you do have to remember, though, is the placement of variables on your graph. The manipulated variable always goes on the x-axis, and the responding variable always goes on the y-axis. That way, your graph shows you what effect the change in your manipulated variable has on your responding variable. Does it make it go up? Does it make it go down? Does it have no effect at all? Okay, does it just stay the same all the way along? Okay, that way the graph tells you that in a kind of quick visual reference. And of course, that's the purpose of a graph. Okay, well, actually, there's more than one purpose to a graph, but that's one of them. Okay, when you look at a graph, you can very quickly see the relationship between two variables, right? From that graph, you can calculate further things. You can get quantitative kind of measurements and relationships, but at least visually speaking, it gives you a very quick reference as to what happened in an experiment, right? So that's the purpose of making a graph, is to give a quick visual representation of your data. Okay, a graph always needs a title. Okay, that title always goes at the top of the graph, and it should be more than the two variables on the graph. Okay, I get a lot of people who just hand in graphs that are like position versus time, acceleration versus time, or whatever it happens to be, but they just they don't put a lot of thought into what the title should be. The title should describe what that graph was showing. Yes, it was a graph of position versus time, but it was a graph of position versus time for a turtle crawling along the beach. Okay, it gives somebody the context at which to look at that graph. If I'm looking at that graph and it says position versus time, and I look at it and go, wow, I wonder what that was. Whatever it was kind of slow. Okay, I'm not going to know it was a turtle. Lots of things are slow. It could have been an ant on your driveway. It could have been anything. Okay, so your title should include some sort of context about the graph and the data that's on it. Okay, is everybody following me there? Right, so your title should be a descriptive phrase that describes the relationship being shown. And I'll show you how to put that title on your Google Sheets graph as well. Now, luckily for you, you will not have to worry about scale because Google Sheets will spit that out for you. Scale always tended to be the hardest part for people. Picking a scale that would make all of their stuff fit on the entire sheet of graph paper. Okay, what I used to get was people who had to have a graph that went, let's say, from a time of 0 to a time of 20 seconds, and they would end the graph like here. Well, what a waste of paper. Okay, there was all this perfectly good graph paper over here that didn't get used. And then on top of that, their graph ends up being squished into this area when it could have been more spread out over a wider area. Okay, you guys aren't going to have to worry about that because, like I said, the computer is going to spit out the proper scale for you anyway. Okay, so we don't have to worry about any of this stuff to do with scale. What you do need to worry about, at least with scale, is when you're looking at a graph, make sure you understand what the scale is telling you. Okay, is it, what is each square worth? Is it worth 1? Is it worth 20? Is it worth 150? What is each square worth? Okay, and obviously each square has to be worth the same amount all the way along. Okay, so we don't have to worry about that. The point 0, 0. Okay, that is called the origin. Not all graphs start there. Okay, lots of people just, every time they draw a graph, they feel like when they put a line on there, it's got to start at the origin. It does not. Okay, many graphs, most graphs, do not start at the origin. And by graphs, I, by the way, guys, mean line graphs. Okay, like a scatter plot of points with a line through it. Okay, not a bar graph or a pie chart or anything like that. Okay, we're talking about a line graph here. Okay, so the point 0, 0 is called the origin. Okay, and it essentially shows the intersection of 0 and 0. So if my manipulated variable was the length of time I'm going to water a tree, okay, and the height of the graph was the let's say the number of leaves on the tree, they would start at 0, 0 when I put the seed in the ground. Okay, because it would have a height of 0 and it would be the first day. Okay, so it would be day 0 and that's where it would meet. Right? The reason I say not all graphs need to start at 0 is I could have a graph whose points go like this. Okay, that's showing an inverse relationship. That means that as the manipulated variable gets bigger, the responding variable is getting smaller. Okay, so if I'm drawing a line that shows the relationship on my graph, that line should go like this and follow the trend of my points. If I started at the origin, it goes like this, and that definitely doesn't say the same thing, does it? Okay, so the origin is just there. It's kind of a reference point more than anything else. Okay. I don't know why I bothered erasing that. I wasn't going to use it again. Anyway, okay, it's Monday morning. Finding the slope of the line. Okay, we're going to do something a little bit different now. Okay, we're going to use this formula. How many people have used that in math? Okay, it's usually about half. Half of you are taking math, half of you aren't probably. Okay, y equals mx plus b is known as the graphing equation, okay, because it is applicable to all linear graphs. That is, graphs that have a trend that is a line, okay, or at least close to a line. So let's say I've got a line graph of position versus time, because that's kind of a simple one that we're going to use. I don't know, we'll say race car or something like that. So we've got a context, okay? Then time is my manipulated variable. It's going to go on my x-axis. Now, sometimes people go, time manipulated, Mr. Coder's Doctor Who. He can travel forwards and backwards in time or what? No, I'm not. I'm not manipulating time. I'm not making time run faster or slower or forwards or backwards. I'm just seeing what the effect of allowing something to happen is. Okay, time is just going to flow. What's going to happen to the race car? Okay, as time flows forwards. So time is the manipulated variable because I choose how long I measure what the car is doing for. In that way, I'm manipulating time. I'm determining how long the experiment is. Okay, does everyone follow me there? So whenever time is on a graph, it's almost always the manipulated variable, unless you're doing some sort of time travel experiment where time might change somehow, other than in the way it normally changes. Okay, normally time does not respond to anything else. Everything else responds to time. Okay, so I've got time on this axis here, and we'll say it's in seconds. And always, guys, you got to have units. Okay, so when you're putting labels on your axis in Google Sheets, include units. Okay, the time is in seconds. Okay, and then up here we're going to have position. So essentially where the car is, measured in meters. Okay, everybody with me there? I'm not going to put a scale on here just because we don't really need it. But so let's say that my points go something like this. Okay, are they generally linear? All right. When I plot them on Google Sheets and I tell Google Sheets to draw me a line, it'll draw me a best fit line. Okay, it's not going to connect the dots. Days of connecting dots are over. Okay, they're not going to make a pretty picture that's somehow hidden in the numbers on the dots. Okay, nothing's going to happen like that. It's just a line that shows the trend of your points. Are all the points going to end up on the line? Nope. In fact, lots of times, none of them end up on the line. That's fine. The line is showing their trend or kind of their average as opposed to trying to actually put them on the line. So I'm going to draw a best fit line with the line tool. That generally follows the trend of my points. Sometimes in math, they'll tell you should have the same number of points above the line as you have below the line. We can tell you that in math, but in science, we don't really like that rule very much because sometimes it just doesn't work out that way. But does that line generally follow what my points were doing? Okay. Now, for y equals mx plus b, it deals with some things that might be on this line. Okay, so what I have with this line is I have a point where the line crosses the y-axis. This is the y-axis and this is the x-axis here. Okay, there's a point where my line crosses the y-axis right here. Anyone remember what that's called? Nope. It is called the Y-intercept. It is where your line intercepts or intersects the y-axis. Okay, it's essentially what y was, or what the position of the car was at time what? 0. So where the car started. Okay, so it didn't start at a position of 0, it started up here somewhere. Okay, maybe it got a head start on some other cars, something like that. Okay, so this is called the Y-intercept, and you might just want to draw like a quick and dirty representation of this somewhere in your notes. Okay, because I don't think it's really in there. Okay, we've changed how we do graphing last year, and we just haven't updated the notes package yet. Okay, so we have our Y-intercept. Okay, and that is also represented as b, which you see in the equation y equals mx plus b. Okay, so that number is part of the graphing equation. It is b. Okay, whatever the y-intercept is, that's b. Y and x are the values of any point on the line. Okay, can they be values of the points you plotted? Only if those points are where? Exactly on the line, which they almost never are. So they can never be, essentially, y or x values from any of the points you plotted. Like this point, it's not really on the line. It's close, but it's not really on the line. This one's definitely not on the line. That one's definitely not on the line. And this one misses the line as well. Okay, so what I need is a y value or an x value that is on my line. Okay, so let's say I'm dealing with this point right here. Okay, it would have a y value and it would have an x value. Okay, and there's a whole bunch of those. There's a whole bunch of those points on the line, okay, that have an x value and a y value. Okay, the beauty of this equation is that once I have my line and my slope, I can calculate y's and x's that are past the end of my graph. It's what we call extrapolating, using what's on my graph to predict what might happen beyond the graph. Okay, so what does M represent? No, Y is position, right? Position values are on the Y-axis, so Y in this graph is position. X on this graph is time. So Y and X represent different things depending on your graph. Slope. M is the slope of your line. In other words, how steep is the line? Okay? Slopes can be positive, like this one is, or they can be negative if your points go down. Okay? Then the slope of the graph would be negative, indicating that whatever you're dealing with is getting smaller. Okay? On this graph, okay, the slope of the line is telling me the relationship between the position of the race car and the time of the race car. What did we learn last week that is the relationship between how far an object goes and how long it takes? Speed. Yeah, speed or velocity if we're dealing with the vector ones, right? Okay, so the slope of this line is going to tell me how fast the race car is going, because it'll tell me how many meters it goes every second. Okay, it's going to tell me the rate at which the position changes over time. Okay, or how many meters it goes over time. In other words, V equals D over T. All right. If I need to manipulate this equation, and lots of times I do, because usually I want to find slope. Okay, how would I get M by itself here? Okay, I would subtract b because this is where we're going to use that half rule. Okay, remember our 2.5 rules of algebra. Okay, if I want to move something, I do the opposite. What I do to one side, I do to the other, and move what's not attached first. B is not attached to m right now. Everybody with me there? All right, so I'm going to subtract. Sorry, I'm just going to draw it down here again. So I've got y equals m times x plus b. All right, so I'm going to subtract b from both sides. Okay, that's going to give me y minus b equals m times x. Everybody all right with that? Okay, now how do I get m by itself? What do I have to do with x? Divide by x, right? Okay, so to calculate the slope of a line, you go y minus b divided by x. In other words, you're taking the change in y and dividing it by the change in x. Everybody follow me there? The change in y is displacement or distance on this graph. And the change in x is the change in time. Okay? It's like that for any graph. Okay? That's why the slope of the line tells us so much on any graph that we have it on. Okay? Sometimes it'll be velocity, sometimes it'll be acceleration, sometimes it'll be coefficient of friction, okay, or basically any number of things. Okay, it tells us a lot of important things about the relationship between the two things on the graph. All right. Now the reason it's sorry, how many people have done like rise over run? How many people have done that or heard of rise over run before? Okay. This is the same thing. Okay, this is rise over run as well, because if you've ever done rise over run, you were told it's y2 minus y1 over x2 minus x1. Does that look familiar to anybody? Okay. Some people teach it this way, some people don't. I'll show both. Okay. If I'm looking at that and at this, it's the same thing. Okay. This would be y2. B would be y1. This would be x2. And what's x here? 0. Okay, so really it's the same thing. Y minus b is the change in y, y2 minus y1, over x, x2 minus x1, but x1 at b is 0. Okay, so it's the same equation, but y equals mx plus b is more, oh man, I just totally drew a blank on the word I was looking for there. No, not common. Versatile. That was the word I was looking for. Okay, it's more versatile. I can use it to do more things than rise over run. Rise over run will only calculate slope. That's all it'll ever give you. Y equals mx plus b will allow us to do more than that. Okay. All right. What if I wanted to manipulate y equals mx plus b to solve for x? Again, subtract b first. Okay, so I'll have y minus b equals m times x, and then what do I do with m? Divide by m. Y minus b over m will give me x. Okay, those are the manipulations that you're going to have to do of that equation. Okay, and we'll start setting up some situations on kind of what kind of things we can calculate from there. Okay. All right. Okay, so what we're going to do is we're going to go into Google Sheets and we're going to build a chart that has these two variables on it, and we're going to build a graph of it. Now, in this chart, okay, we're going to be graphing diameter and circumference. Which one depends on the other? Circumference depends more on diameter. What we're trying to find out is what is the relationship between diameter and circumference. So as I increase the diameter, circumference also gets bigger, right? Because they're dependent on each other. So what we're going to do is we're going to build a Google Sheet of that right now. Okay, so I want you guys to open up Google Sheets, okay, on your Chromebooks there. All right, so I'm just going to open up a blank one, so basically a new one, a new thing. It's going to look like this. Okay. And when I start building something in Google Sheets, okay, what I want to do is label the columns of data that I'm making. Since diameter is going to be my manipulated variable, and I want it to end up on the x-axis, it needs to be listed first. Okay, so my first thing here is going to be diameter. And I'm going to put the units in there. It's in centimeters. Okay, and my next column is circumference. And it's also in centimeters. Okay, now you'll notice that that doesn't always fit. You can just click on the little lines between them, okay, and drag it over a little bit if you need it to be bigger. Okay, our next step is enter our data. Okay, so I need to enter our circumference and diameter data. I'll blow that up in a minute here, guys. I just need to be able to see them both, or you can enter them as I enter them here. So my first diameter is 1.8 centimeters. Okay, my second diameter is 2.8 centimeters. My next one is 3.2, then 4.4, and then 6.6, and then 7.4. All right, then I'm going to go over and fill in the circumference data, 5.6, okay, 8.9, 10.2, 13.8, 20.6, and 23.1. Okay, what did I not put in with any of these numbers? I didn't put any units in there, and I did it on purpose. They're up here in the label. If I put them down here, Google Sheets gets confused, and it won't graph stuff because it's got letters and numbers in the same box, and it doesn't know what to do. Okay, it doesn't know how to represent a letter in a graph. Everybody follow there? Okay, so never put units beside your numbers in Google Sheets. Put them in the label at the top of the column. Okay. Okay, I'll let you guys get the numbers written down there or copied in. All right. Our next step, you got to highlight all of the stuff in your sheet right now. Okay, so click on the diameter box, click and drag until you've highlighted all of it, and it all turns blue. Okay, then we're going to go to Insert. Click on that and go down to Chart. Okay, click on that, and it's going to spit out some recommendations. It never recommends the right thing. At least in my experience, it has never recommended the right graph type. So I'm going to go over here to Chart Types, which is the next one over, okay, right here. And then I'm going to scroll down until I get to Scatter, XY Scatter, right here. Okay, click on that, and it spits out a scatter chart, which is exactly what I was looking for. Okay, then you can see here it's already checked use row 1 as headers, which means it recognized there were no numbers in the first row and that it shouldn't try and put that in the graph, okay? That it recognizes their labels and that it's not going to put them in there. All right, then we're going to go to customization. And this is where we can put in a proper title and labels on axes and things like that. So if we go to customization, the first option is title. All right, so rather than have diameter and circumference, okay, which is fine, I probably want that in there, I'll put in versus. And then I might also call it circle graph or something like that. Okay. And you can change all kinds of things about the title. You can change the size, you can change the color, you can bold, italicize, do whatever if you want. Okay, I'm not going to change any of that right now. It's fine the way it is. Okay, now we're just going to grab the scroll bar here and move down a little ways until we get to the part that says axis. Okay, right now, anything we change is going on the horizontal or X axis. Okay, so we click in title here and we click what, or sorry, we're going to type in, what do we have on the X axis? Diameter, right. Okay, so we're going to go diameter in centimeters. Okay, so a label with units. Okay, and you can see once you click away from there that it updates it. Other things you can do is you can choose your grid lines, major and minor. Okay, it doesn't matter what you pick. Sometimes I like to make my graph look really busy, okay, and have lots of lines on there. It doesn't really matter which way you do it. Okay, so that's down there on grid lines. What I'm going to do now is click onto axis up here where it says horizontal so that I can get left vertical because I want to change, I want to put a label on my left vertical axis as well. Okay, and that was circumference. And that was also in centimeters. Okay, and I can do the same thing with the grid lines if I want to. Then it looks more like graph paper. It's got more grids. Okay, everybody caught up with me? Okay, so we're going to scroll down a little further now because so far we don't have a best fit line. Okay, we haven't put one on there yet. Google Sheets will draw one for us if we tell it to. Okay, the next thing you see down below here is series, which is just where you can name if you have more than one series. So let's say like in a few days when we do our graphing lab, we're going to be graphing 4 cars on the same graph. Okay, well, we might want to change what the points look like, change their color, things like that, just so they look different. And then you can change, it was car 1 or car 2 or whatever. Okay, that's where you do it, is right here in the series. Okay, and you can change them to whatever. All right, error bars is not something we ever put in, but you can see right here at the bottom it says trend line. Okay, that's what Google Sheets calls a best fit line, is a trend line. Right now it says none. So if I click on that, it gives me 3 options basically: linear, exponential, and polynomial. What kind of a relationship am I looking at on this graph? Linear. It's a line. As one goes up, the other goes up. Okay, so I'm going to just click on linear, and it draws me the best fit line. And every one of my points happens to be on it, which it should, because there's kind of a fixed relationship between diameter and circumference. What is that relationship? Pi. Exactly. What should the slope of my line be then? 3.14. That should be the slope of my line, because that's the relationship between diameter and circumference. All right, let's find out if that's the case. Once we put in that linear thing, we get more options when we scroll down. Okay, the one is label. Right now it says custom. That's no good. We don't want that. We want it to spit out the equation for this line. So we click on use equation. Okay, so what are we seeing here? Y equals some number times X plus another number. Okay. So Google Sheets spits out for you and does all the work for you in terms of drawing the line correctly and calculating the slope for you. It also tells you what the Y-intercept is. So the 2 numbers that we see here, okay, Y equals 3.103. Okay, it didn't come out to exactly pi. Any reasons why it might not have come out to exactly pi? Yeah, it has to do with the person who measured the values. They may not have measured them perfectly accurately. Okay, and so as a result, they're not going to get exactly 3.14. When I've drawn this graph by hand a few times, okay, I've gotten close. I've gotten 3.14 once. Okay, but most of the time it ends up being around 3.1. So it's close. We have to go with whatever measurement was made for us. Okay, and it's telling us that the Y-intercept is positive 0.149. There's where we know there was a mistake in the person's measurement. Because they're saying that a circle with a diameter of 0 has a circumference of 0.149. centimeters. Is that possible? If you don't have a diameter, you don't have a circle. Okay, that really should be what? 0. Okay, it doesn't come out that way, but it really should be 0. All right, so now we've spit out here, okay, our equation. Now, what we want to do is insert that graph. Okay, it's all done. Okay, we've got our labels on it. It's got its equation on there. Okay, so let's click insert. Okay, so there it is. Now we've got our graph. If we want to, like if we're doing a lab report, we can now copy this over into our Google Doc where our lab report is being written, which is what you're going to have to do with graphs when we build them in Google Sheets, is pull them over and put them in Google Docs. Okay, so what I would do is I would just open up a Google Doc. If it ever opens. Okay. Then I would take this thing here and I would just copy it by clicking on that. Okay, click on the little triangle there at the top, copy chart, go over to my untitled document. And it's this is a new feature in Google Sheets and Google Docs this year. Link it to the spreadsheet, which means if you get it into your lab report and then you realize it's not right, go back into Google Sheets and make changes, and the changes appear magically over on the graph in Google Sheets. You don't have to delete it, recopy it. Okay, if you just link it, any changes you make, okay, will appear in here. So if I go back now, let's just say I'm going to change one of the points here. I'm going to go and I'm going to add in another point. I'm going to put in 0 and 0 and see if that changes anything. Look at that. See, it changed my slope from 3.10 something to 3.117 now, getting a little closer to pi. Okay, let's see if it changes it over here. Update. Done. Okay, so you wouldn't have to do much more than click the update button, okay, when it appears on there, if that ever happens to you. Okay, it's a nice little feature that they put in this year. Okay, everybody follow how that worked? Austin, question? I'll have to come over. It's got to be something to do with the numbers you entered. Okay. All right, so here's what I want you guys to do. I want you to click on the plus sign down here at the bottom of the page where it says add sheet plus. Okay, so a new sheet will appear, and I want you to build that graph. On this one, the length of the elastic band is the manipulated variable. Okay, so the length of the elastic band is the manipulated variable. You should do this column first, so it appears on which axis? The x-axis. Okay, so the length of the rubber band is the manipulated, force on the elastic band is the responding. All right, so now that I've got my data entered, force is going to be on my x-axis and length is going to be on my y-axis. I highlight everything, okay, and I click Insert. I go to Chart. I want a scatter plot, so I click Chart Types and go down to Scatter. Click on that, and I get this pattern, which is great. Okay, for customization, force on band, I might just shorten that to something else like. Okay, force versus length. And then I'd go down and put on my axes here. So my horizontal axis is going to be force, and the units for that are newtons. That's why it's an N. Okay, and then click on the left vertical, and the label on that is going to be length of band, okay, in centimeters. Okay, I can put more grid lines on, but I don't need to for this one. I'm going to keep my points I mean, I can make them whatever I want. I could make them stars and make them pretty. Doesn't matter. Okay. Then I'm going to go down to trend line, click on linear. It draws the line. All the points are pretty much on the line. And now I want it to spit out the equation for me. Okay, which it does. And it says that y equals 2 times x plus 6.5. Okay, so I'm going to click insert, and then we're going to look at what this graph is telling us. So b, which is called my what? Y-intercept, is 6.5 on this graph. What is that telling me about the rubber band? It's 6.5 centimeters long when it's not stretched, or the unstrained length of the rubber band is 6.5 centimeters. That's what the graph is telling me. Of course, my data kind of told me that too, okay? But the graph is certainly saying the same thing. What else is this graph telling me from a numbers perspective? Exactly. It's telling me how many newtons of force I need for every centimeter, or sorry, it tells me that every 2 centimeters of length stretching is going to require 1 newton of force. 2 centimeters per newton is what my slope is, okay? Because when I take y in centimeters and divide it by x in newtons, I get the units of centimeters per newton, okay? And it's telling me that every 2 centimeters requires 1 newton of force. Okay, we're actually going to do an experiment kind of like this, okay, a little bit later on in the unit where we'll get exactly this kind of graph. Okay, except that ours will be switched. That's why I had it switched in my head, because I was thinking of that graph where it's actually the other way. Okay, where we're going to calculate the amount of work done in stretching a rubber band. Okay, so we'll do kind of the same experiment that they're doing right here. Okay, now an application using this graph. Okay, so I'm going to go into the Smartboard software again, so you might want to write this down on your sheet, okay, because it's going to be kind of an additional problem to do with this graph. Okay, so the equation that got spat out for us is that y equals 2x plus 6.5. Okay, that's what Google Sheets said. How long will the rubber band be when there is 20 newtons of force applied to it? Okay, so let's just write this down as kind of a sample problem. Okay, that number isn't on my chart. That number isn't on my graph. My graph only goes up to 11 newtons. Doesn't show me anything beyond that. No, it's not going to be 40 centimeters. 46.5 centimeters. But here's how we calculate that. This is, I know a few people just kind of thought of that logically, okay? But here's how we got to do that mathematically. I'm looking for length of the rubber band, which is a y value or an x value? It's a y value. Length is on the y-axis. So I'm solving for y. What's x going to be? 20 newtons. Because on the x-axis is where force is. I was given an x value and asked to solve for its corresponding y value. So if I go back to my graph here, which is there, and you know what, I'm just going to copy it over real quick. Not what I want. I hate how everything is laid out now. This is taking way longer than it should. Okay. Not cool. Not cool. Stupid. Ah, my graph is gone. That's not the right graph. Oh, I'm going to lose my mind. I hate Mondays. I hate them. What? I actually did what I wanted. That's a terrible lesson to teach you right there. Okay. Into a new page in Smart Notebook. Yes, that's what I want. Okay, so here's what I've got. Okay, this is my graph. As you can see, it only goes up to 12. What I'm looking for is like way over here at the top corner of the screen, not on my graph. I'm doing what's called extrapolating. I'm extrapolating from my graphing equation for this relationship to a value not shown on my graph. So I'm looking for an x value of 20 newtons and seeing what the y value for that would be. Okay, so now I'm going to get rid of that because I don't want it anymore after all that work. Okay, and I'm going to go back to this. I'm solving for a y value, so do I have to manipulate it all? No, I just need to plug in the numbers. So that's going to be y equals 2 times 20, the 20 newtons, plus 6.5 centimeters. Okay, that's where the 6.5, I have to account for the initial length of the rubber band, right? It's going to be that, this much is how much it stretches. This is how much it was before, and I have to add the two together. Does everyone follow that? Okay, so it kind of makes sense. So we're going to get 46.5 centimeters as the length of the rubber band when 20 newtons of force is applied to it. Okay. What else could I ask you from that graph? Awesome. Right. So that's the other way we're going to look at now is I'll ask you, let's say, using this equation, how much force is needed to stretch the rubber band to, let's say, 60 centimeters. Okay, so y equals 2x plus 6.5 was the equation we were given. Okay, so now I'm looking for y or x. I'm looking for x because it gave me a y value. It gave me the length, which is on the y-axis. So I know y equals what? 60 centimeters this time. So now I've got to solve for x, which means I do have to manipulate just a little bit. All right, so I'm going to bring the 6.5 over here by doing what? Subtracting. So y minus 6.5 equals 2 times x. Okay, how do I get x by itself? Divide by 2, right? All right, so that's going to solve for x. So I'm going to plug in my 60 centimeters now. Okay, that was the y value I was given, minus the unstrained length of the rubber band, 6.5 centimeters, divided by the slope. Okay, now here's why this is going to work. The top's in centimeters, and the slope is in centimeters per what? Newton. So the centimeters are going to cancel, and I'm going to be left with the units that should be on an x value for this graph, newtons. Okay, so we'll have 53.5 over 2. Okay, so we're going to have a force of 26.75 newtons. Okay, and that's really all you'll ever be asked to do with a linear graph. Okay, is be able to identify What am I looking for? Y or X? What was I given? Y or X? Manipulate the equation, solve for Y or X. Okay, because a software like Google Sheets is always going to spit out for you M and B. Right? You're almost never going to have to solve for M or B. Are you going to have to understand what M and B represent? Yes. Okay. M is always the slope, but the slope represents different things based on what kind of graph you're dealing with. Okay. And B represents different things depending on what's on the y-axis. But remember that B is always a y value. All right. So whatever y is, B is the same thing. Okay. In terms of units. Okay. If y is in centimeters, B is in centimeters. Okay. Add another sheet, guys. And I want you to do that one. In this case, the thickness of the book depends on or responds to the number of sheets. So what goes on the x-axis? Number of sheets, right? Yes, so these have all been backwards for you. What equation got spat out for that? 0.15 x plus what? 5? Okay, so what we're looking for, guys, is the thickness of a book with 300 pages. So what am I calculating, a y or an x? A y, right. Okay, so that means I'm going to have 0.15 times what? 300. X was 300. I told you the number of pages, okay, or number of sheets. So X was 300, okay, plus 5, right? So 0.15 times 300 plus 5. All right, so it will be 50 millimeters thick. Okay, everybody follow there? Yes, you would have to put 50 millimeters on that. No, there's no units because it says number, right? So we know it's just a number. Okay, and what about if I asked you how many sheets a 90 millimeter thick book would have? What are you looking for then? Then you're looking for X. Okay, so we would manipulate, right? And we would have 90 minus 5 over 0.15 would give me X. Okay, so we'd have 85 over 0.15. Okay, so it would be 566 pages, 567 pages. Okay, would be how many pages there would be. All right, is that making sense? How to use the equation? The equation is not hard to manipulate. It's actually pretty straightforward. It's just a matter of can we recognize on any graph what it represents. Okay. All right, if I can get you guys to start shutting those down and putting them back on the cart here, that would be much appreciated.